Alright, gang, here we go. This is for Chem 1, Unit 13, Part 3. We're talking about factors that affect reaction rate. Alright, so just to recap, we've talked about how we use the collision theory, the collision theory, to determine whether or not a reaction will take place. And essentially what this means is that in order for a reaction to take place, you have to have the reactant molecules collide. But then when they collide, they might not make an effect of a reaction. But when they do collide, and they cause a reaction, we call that an effective collision. An effective collision. And so those effective collision that occur, they need two things. Number one, they need to have enough energy. Enough energy. All right. To meet the activation energy, right? And we talked about the activation energy in the last video. And then also they need the correct orientation. So in order for you to have a reaction, these reactant molecules need to run into each other. And when they run into each other, they need to have these two things met. They need to have enough energy, and they need to be in the correct orientation. So essentially, anything that we can do to increase the amount of collisions, or the amount of effective collisions specifically, it will raise the reaction rate. And anything we can do to lower the amount of collisions would lower the reaction rate. All right, so a couple of them are fairly obvious right off the bat. Temperature, remember temperature is a measure of the kinetic energy, of the average kinetic energy of the particles. Right, so if we want to get an idea of how fast these reactant molecules are running, or reactant atoms, or whatever they may be, we just have to take the temperature, right? And the higher the temperature, the faster they're moving. Well, if they're moving faster and faster, you can imagine if you hit if you're breaking in billiards, right? You're the first one. You're breaking the rack, right? And if you hit that rack really hard, those balls are going to go everywhere very, very quickly. You're going to have a lot of collisions, and there's a lot more chance to have one of those balls end up in the pocket. Whereas if you hit it really, really lightly, they're going to be moving a lot slower, fewer collisions, and a lot less chance of an effective collision, meaning a ball goes into the pocket. And same idea here works with reactions. Chemical reactions is if they're moving a lot faster, these molecules are going to be moving more, and so therefore they'll collide more often. So their collisions are more frequent. But at the same time, they're also more energetic. So not only will the collisions be more frequent and more often, but they'll also have more energy, and therefore more often they'll have enough energy to meet the activation energy. All right. The second thing we can do is increase the concentration. If we increase the concentration, it'll increase the reaction rate. All right. So remember, concentration is usually, we'll think of that in terms of molarity, which is in moles of our solute per liter of solution. And so the higher your concentration, the more moles of your reactant molecules you have. And if you have more of those reactant molecules, they'll hit each other more often, and so they'll have more likelihood of having an effective collision. Therefore, your reaction will get quicker. So they'll have more concentration as more particles, therefore more frequent collisions. All right, and then we could go the other way. If we decrease concentration, we'll have less particles, and then therefore there will be less effective collisions, and so a slower reaction rate. Next thing we can do is agitation. Just essentially stirring or shaking, mixing in some form. Would increase the reaction rate, because essentially what we're doing is we're making sure that these molecules, the reactant particles, will hit each other more often, right? And ensure that they'll have more collisions with each other, and then therefore if you have more collisions, you'll have more effective collisions, and therefore your reaction rate goes up. And then same thing if you have something that's if we have something that we're just letting stay stagnant, that doesn't get mixed, your reaction rate will go a lot slower. All right. Next one here is particle size. Essentially, if we take if you imagine you've got a piece of wood, right, and it's a log, right, and you want to light it on fire, it'll be pretty hard because the only place that that wood can burn is where it can mix with the oxygen, and the only place it can mix with the oxygen is right at the surface. There's no oxygen down amongst the wood. But if you take that same piece of wood and use, a sander, sand it off so it's a big pile of wood, and then you can disperse that wood so it's taking up a bigger volume, right? But there's air mixed among it. You blow that sawdust up so it's bigger, you can have more oxygen mixed around it, and therefore you can have more area for an effective collision occur. Again, essentially, if we increase the amount of places that an effective collision can occur, therefore we'll have more effective collisions. All right, so increasing the surface area will increase the chemicals that are exposed to react. So therefore, more collisions. All right, we can also decrease surface area by making it, closed in, taking that sawdust and making sure it's piled up in a pile on your table, and if you try to burn that, it won't burn quite as effectively as if the sawdust was dispersed in the air. All right. Last one here that we can do to affect our reaction rate is by using a catalyst. We talked about catalysts very briefly in the previous video, but a catalyst is a chemical that increases the rate of a reaction without being used up itself. So essentially what it means is so say you have some reaction where it's like A plus B yields C plus D, right? This is our reaction mechanism, so this would be step 1, and then step 2, and then C plus E yields A plus F, whatever, right? Our overall reaction, right, would be, we could cancel out what doesn't work here. So this is practice from number 2 here. So the A's cancel, the C's cancel, so we'd have B plus E yields D plus F would be our overall reaction. Now remember, the C's were produced in this step and used up in this step, so the C's are intermediates. Okay, intermediates. C. But our catalyst here, is something that we added at the beginning and we got back out at the end. So maybe I'll draw a line to make sure it's clear that these are part of this one. So anyway, so this A value here we started with at the beginning and then we got it out at the end. Okay, so it was in both. Okay, so catalyst is something that we can add to increase the reaction rate, but it doesn't get used up. Essentially, we could take that A, put it back with another B, and use that, and we'd get that A back out again. And we can continually use that A. We don't have to keep giving more and more and more A. So catalysts are pretty special. Okay, a lot of times when you're doing a reaction that uses a catalyst, it's written above the reaction arrow. Otherwise, if you try to put it as a reactant, that doesn't make sense because it also comes out as a product and it doesn't really get used. But putting it above the reaction arrow is what it's usually written as. So if you see, so in this case, SO2 plus O2 with that platinum, that means that platinum is a catalyst. All right. Now, generally, what the catalyst does, just very briefly, is that they work because they lower the activation energy. Remember that activation energy is the amount of energy it takes to reach the activated complex. So here in this energy diagram, we've got energy and reaction progress in the Y and the X. All right, here's your reactants and your products. All right, and your activated complex is up here where I put this X. Now, normally the black line here, this is when you're not using a catalyst. So your activation energy is really, really high. Look how much energy it takes to get that reaction started. When they added the catalyst, it changes the pathway, it changes this mechanism. And so it uses a lot less activation energy. And so our activated complex for the catalyzed reaction is down here. All right, and so the activation energy is much, much, much smaller. All right, so that's generally how they work. So, but notice here that the energy that we get out of this change in energy or enthalpy, all right, what we get out of our reaction is exactly the same whether we use a catalyst or not a catalyst, right? We end up, the energy to the products is the exact same difference. All right, so that's it. We talked about 5 ways we can influence our reaction rate. Right, and so make sure you know how to do those, be able to explain both how we can use them to speed up and slow down a reaction, and so on and so forth, and kind of generally how they work. Anyway, so do your practice problems, let me know if you have any questions, and I'll see you on the flip side.